Welcome, this is the VO2 Lounge, episode 63 on cycling aerodynamics. In elite cycling, the resistive force is dominated by aerodynamics. Be it on the roads or in the velodrome, the sport has many examples where aerodynamics has won and lost races. Since the invention of the bicycle, engineers have strived to improve performance, often by reducing aerodynamic drag, for this very reason that it is the dominant force opposing the rider's forward motion, essentially. Now, we've done supplements recently. This episode I was going to do something on aerodynamics, mainly because myself, coming to the end of the season, anyone in the Northern Hemisphere probably only has one or two, if any, races left. And so I'm looking forward about how to improve my performance, making notes. Obviously, you've got the training component, but to be honest, for me, the training component is trying to increase the volume, which I did last year at that time of year. So say, for example, it was 5 hours for someone during the winter and then they come up to 10 during the summer, going from 5 to maybe 7, 8, 9, or trying to keep that 10-hour volume throughout the winter, however you manage to do that, which isn't always easy in the Northern Hemisphere with the weather we have if you don't like indoor training. But then the next component is making the most of the watts you have, especially if you're into your third year, fourth year of racing. You know you can't increase volume, so all you can do is optimize the intervals you're doing. And if you're already doing that, really, the big one is aerodynamics. If you're racing and you're averaging 40, 45k an hour, there is, even in the bunch obviously, but if you go off the front, for example, or even in the sprint, aerodynamic drag is playing a huge role in your end speed. And if you're someone who is getting into brakes because they're more of a steady state human being, when you're on the front, you know, there's a lot of energy going into being lost in aerodynamic drag. So for all the marginal gains that there are, whether it's lube on chains, tires, less, I say marginal, it could be a huge gain going from, let's say, some steel bead Vittora that comes on a 1,000 pound bike and going to a GP5000, but wondering whether you're going to run a GP5000 or a Vittora Corsa G2 Pro, whatever it's called, are marginal, whereas maybe you're racing not in a speed suit, maybe you still have a heavily vented helmet, maybe your position's off, maybe your bike could do with some adjustments. This is where aerodynamics come in, and now's the time to really work on that new position, investigate into new equipment, and so on and so forth. So let's get into this episode where we're going to kind of go over aerodynamics in general, and we're going to go through mainly the function of individual components, less as much exactly how many watts you're going to save, because really a lot of it comes from wind tunnels and less outdoor or velodrome, for example. Really, you know, at the end of the day, the speed improvement is the key metric we're looking for here, and especially things like helmets, which we'll get onto, incredibly individual specific. So, you know, we're not going to go too much into, this is 2 watts and say that this is empirically 2 watts. We're just going to kind of go through what the function of them are, the level of value, I suppose, in each individual point, and what are kind of the best practices for optimizing your aerodynamic package and improving performance in that manner. I mean, let's look at the hour record, for example. Obviously, Dan Bingham had it somewhat brief period of time, but he had it, and he surpassed Bradley Wiggins at the British hour record. And the fact that an individual who's, you know, doing, just say in general, somewhere between 340 and 360 watts for the hour versus people are doing north, and Ghana, who surpassed it, doing north of 400, identifies the fact that, you know, Aero is playing a big role. And obviously it's north of 50 kilometers an hour. The speed at which you're optimizing for there is different to the road, and the level of drag lost, or the level of time, speed, whatever you want to call it, the energy lost to drag is obviously exponentially higher at that versus 40k an hour, but it puts emphasis on the fact that you as an individual could reach a higher level simply through an optimization in your aerodynamic package if you haven't already gone down that avenue. But enough jibber jabber from me for now. Let's get into this episode and discuss a general overview of cycling aerodynamics. So the fundamental physics that govern a cyclist's motion are well understood in general and have been extensively modeled in literature. A notable example, which was new to me, to be honest, is the mathematical model for cycling power validated by Martin et al. This model accounts for several factors that influence the power output from the rider, which is transferred then to the wheels through the cranks via, for example, the chain, which then has an efficiency. The model includes the effects of aerodynamics resistance, rolling resistance, from the interaction between the tyres and the road, wheel bearing friction, potential energy changes when cycling uphill and downhill, and the inertial effects essentially due to both linear and rotational acceleration. So aerodynamics, really, the aerodynamic power is the most significant component of all of this and can be split into two parts: the resistive force acting against the cyclist's motion, which is aerodynamic drag, and the aerodynamic forces that oppose the wheel rotation. Now, the aerodynamic drag force acting on a cyclist is influenced by the drag coefficient, CD, and the cyclist frontal area, which is A, which is where you get this CDA that people refer to frequently. It's also dependent on air density, which is influenced by pressure, temperature, and the specific gas constant of where you are, essentially, of air. Now, aerodynamic drag, notably, drag increases with the square of the wind speed, and as a result, the power required to overcome drag grows with the cube of wind speed. Now, this is why I was suggesting earlier in the introduction that the faster you're going is where not power makes less impact, but say, for example, it's a bit like watts per kilo, where watts per kilo up a steep gradient is the dominating factor, whereas watts per kilo on a flat, it's like for most UK races, really, watts per kilo, less of a, you're just trying to optimize your body composition, but really a higher threshold is more important than a ludicrous watt per kilo, because we're not doing 40-minute, 50-minute, hour-long climbs, for example. And the same is the case for aerodynamics, where the slower the event is, the less important it is, because it is exponentially growing with the speed at which you're going. So, for example, someone who is just doing club runs and there's no necessary performance situation, but like a fast ride is 30 kilometers an hour, versus someone who's racing and their race is the goal, and obviously there's performance linked to that, but the speed is 45k an hour. It's not a linear progression. The person at 45 is benefiting exponentially from their aerodynamic improvements compared to the other individual, but it also means clothing, kit, everything needs to be optimized differently for the flow at which occurs during that velocity, essentially. Now, air density varies with altitude, obviously, and temperature and pressure. At higher altitudes, lower air density results in reduced aerodynamic drag, which is why cyclists record records for the hour tend to be done up at altitude. Now, yes, there is that you can do them at sea level, and obviously at altitude you've got the acclimatization part of things, but the net gain is a positive one thanks to this air density change. Now, as I've said, as speed increases, aerodynamics become the dominant resistive force. And on flat surface, aerodynamic drag can account for over 90% of the resistance faced by a cyclist, which is demonstrated by Kyle and Brook in one of their studies. Now, additionally, Martin et al. Showed that aerodynamic resistance contributes between 56 and 96% of the total power, depending on road gradient, and that's to improve performance. Partially in particularly in events where the acceleration is not crucial. A cyclist must either produce more power or reduce their aerodynamic drag to improve their speed, essentially, and more importantly, the more you work on the aerodynamic side of things, the less power you need to do. So if both are increasing, then either you hold a higher speed or you do less work at the given speed. Now, that, as I've said, creates this scenario where the entire rider individual package allows for a broad level of competition. It's why you get people like Remco Evenepoel, very small rider, sort of physiologically fits a TT bike very well, and that's where you get, and even on the road, you see his aero position very compact and looks very, like the angles that are produced look very good for allowing potentially a lot of attached flow across the body, and hence why you can have smaller riders like that who have without a doubt a lower threshold than people like Wout van Aert and Mathieu van der Poel, who are bigger riders, but their part of the equation is, somewhat aero, but the higher power. And then you've got Evenepoel, where you've got the incredibly aero individual, allowing for the competition, and why people like that don't suddenly just get blown out of the water on any kind of flat terrain, essentially. So I promise at some point we will get on to the kit decisions, essentially, which is probably what a lot of people are interested in. However, let's get on to some cycling fluid dynamics, because the purpose of this is just more to, give you some more coffee chat. So when you stop at your coffee shops, rather than just being like, it holds its speed, you can talk about these kind of things. Now, anyway, so cycling fluid dynamics. The flow around a cyclist falls into a category of bluff body flow, which is characterized by the large regimes of flow separation due to the abrupt change in geometry. Unlike streamlined bodies such as aerofoils, which have a smooth, gradual reduction in cross-sectional area that help maintain attached flow, bluff bodies like cyclists have sharp edges and dramatic reductions in body width towards the trailing surfaces. This essentially results in significant adverse pressure gradients that the boundary layer cannot sustain, leading to flow separation and the formation of turbulent wake. Essentially, always the easiest way for someone who, never did engineering or anything like that, to understand what is occurring here is, imagine you've got your hand in the bath and you're pushing your hand, but you've got your palm essentially facing the direction of flow. That big frontal area, followed by a not very large cross-section, essentially, means that the flow itself is very drastically being forced to go round this object, and then is going to want, because of the low pressure behind the object now created, to fall into that space. And that tumbling that you see when you move your hand through the water, that's essentially these vortices and this pressure gradient and this flow separation that's occurring. Because if you looked really closely as well, when you're moving your hand fast through the water's almost being ejected outwards almost. It's not like just passing over the top, it's being forced outwards and then back down. Whereas if you now turn your hand 90 degrees and now the palm is facing down and your skinny part of your hand is now facing the direction of flow, there is a much smaller gradient at which the water now needs to flow around. And so it can simply remain attached. Maybe there is some separation, but it can remain attached. That boundary layer is just essentially the layer of air that essentially remains attached to the surface, the skin, and that isn't disturbed as much. And then when the water now collapses behind your hand, essentially that vortice generated, that tumbling is less drastic. And then that's simply why it's even easier. You probably can feel both the pressure drag, which is the pressure in the frontal area, the front part of your palm. You can feel that build up, but you can also feel like a suction essentially behind the hand. And that should be less apparent when your hand is now turned 90 degrees. But that's essentially a streamlined object. We are not streamlined objects. So we have to manipulate either our body position to become more streamlined, or the equipment we use to primarily improve the attachment of flow to the body. Now, in cycling, the aerodynamic drag is primarily due to pressure drag, as I've just said. Now, as opposed to viscous drag, which dominates in streamlined bodies. Now, flow separation around the cyclist creates large-scale, low-pressure vortices in the wake. Now, the wake, as I said, is that area behind essentially your palm, that disturbed area. Now, this contributes to a pressure differential between the high-pressure station region at the front of the cyclist and the low-pressure wake at the rear of the cyclist. Now, this pressure differential is the key factor in pressure drag. And the aerodynamic efficiency of cyclists is commonly measured by drag coefficient, which describes how streamlined an object is regardless of its size, essentially. If you've ever seen some of these CFD images where you've got like the silhouette, maybe a white silhouette of the cyclist or a car or whatever it is, and then you've got this color scale, and then the front usually red indicating high pressure, the rear usually blue indicating low pressure. That's that pressure differential we're talking about. So if you ever see one of those, that's what that is. Now, the key points of bluff body aerodynamics in cycling. Now, pressure drag, obviously the dominant cycling aerodynamics caused by large region of separation of the flow that creates turbulent wake behind the rider. Now, then the drag coefficient values for cyclists typically range from 0.6 in an efficient time trial position to more than 0.8 in an upright position. You think the upright position, you've got your palm going through the water, bolt upright. And then the time trial position is just essentially bringing that front finger portion of your hand further and further down to as close as a streamlined body to enable as much as and as close to a streamlined body as you can get, essentially. Now, streamlining a cyclist and using equipment such as fairings can significantly reduce the drag coefficient down to values around 0.1 in high-speed human-powered vehicles. We're talking here like these like land speed recordy kind of things, where you've got the bike now no longer truly resembles what you would expect on the road, completely non-UCI legal, for example. Now, pressure distribution on a cyclist's body depends on body shape and position, which high pressure stagnation regions at the front and low pressure wake region at the rear, minimizing the pressure differential by reducing the frontal area or optimizing the body position is crucial for reducing drag. Reynolds number, which you'll hear from time to time, quantifies the ratio of inertial to viscous forces and is a key factor in determining the flow characteristics around a cyclist, such as whether the boundary layer remains laminar or transitions to turbulent. Now, the boundary layer, again, just this very small area along the cyclist. Now, if it's remaining laminar, it means the flow is kind of attached, and that flow is remaining laminar, smooth almost, essentially. Now, whereas the turbulent are easy to understand. You've got separation somewhere, and then because of the pressure distribution, it's falling back on itself. It's turbulent. It's causing more disruption to the pressure distribution around the cyclist, and it's resulting in increased drag. Now, minimizing drag in cycling. Now, reducing drag is largely about controlling flow separation and minimizing the size of the turbulent wake by maintaining attached flow as long as possible and reducing the size of the separation region. The aerodynamic performance can be enhanced quite drastically. Now, in order to prevent early flow separation, gradual surface expansions and curved geometries are used, which allow the pressure to recover without reducing separation. Inducing. This principle explains why low drag shapes like airfoils tend to have long tails, allowing flow to remain attached. And that's essentially like where you get these TT helmets with the really long tail. It's essentially allowing as much time as possible for the air to reattach or gradually come back together post the cyclist, rather than the helmet being very short. It remains attached for a bit, but then the transition at the end is too drastic and the flow collapses like it does behind the palm of your hand. It collapses and causes all that turbulence. And that in itself is where you can see, again, why those TT helmets can be so individual and so important, is because that air collapsing is going to drastically impact the flow attachment on the back of the individual, and therefore a big area that now is no longer laminar and is incredibly turbulent and is going to produce a lot of drag. Now, the goal in cycling aerodynamics is either to minimize the frontal area, thus reduce the area of which the pressure differential acts upon, or optimize the pressure distribution by reducing the size of the stagnation region and controlling the location of flow separation. Now, minimizing aerodynamic drag in cycling becomes significantly more complicated due to the dynamic nature of the cyclist's body, particularly with the unsteady aerodynamics caused by the motion of the legs around the crank cycle. Now, these complexities are further amplified when considering the three-dimensional flow structures that develop around cyclist's body as they move. Really, that's the thing. It's why so you need a cyclist on your bike and with the kit, rather than putting kit on a mannequin, because of that movement. Now, it's also why it's important in, say, a wind tunnel for the wheels to be moving, because the stationary wheel allows for much better flow, essentially the laminar flow across the wheel versus when it's rotating and it's causing utter chaos. It's almost why I wonder, really, a big team, say like Ineos, Jumbo-Visma or whatever, say, you've got Jonas and you want to optimize his TT, but putting him in a wind tunnel or putting him at a velodrome, for example, so much is taking away from training. And if they've got a race schedule and you want to continue the optimization through the year, it's quite hard. So you'd almost want to select a rider, an individual, almost from the public that, can, in the case of a velodrome, can maintain a reasonable threshold, doesn't have to be how it can be little 5-minute bursts. And in the wind tunnel, even easier, and can essentially mimic the position of your elite cyclist, and act as the dummy test. And is it worth it? I don't know, but I think it's probably potentially an area where a team could get some benefits from, in my opinion. Now, this kind of leads on to some insights from some studies on cycling aerodynamics, which talk a lot about the variation in aerodynamic drag during pedaling. Now, research has shown that aerodynamic drag acting on a cyclist can vary significantly, around 20%, through a single pedal stroke. Now, this variation does not primarily come from change in the cyclist's frontal area, which only varies about 2%, but rather the changes in flow patterns and the drag coefficient associated with the wake produced by the cyclist. Now, Now, experimental and numerical studies have identified two primary flow regimes that arise during different phases of the pedal stroke. Symmetrical low drag regime, which occurs when the cranks are in the near the horizontal position. In this regime, the wake behind the cyclist is characterized by streamwise vortices originating from the upper and inner thigh. Now, these vortices are aligned with the free stream direction, so the flow of air, the rest of the flow of air, leading to lower drag because it's conforming to the rest of the uninterrupted stream of airflow. Now, asymmetrical high drag regime is the second. This arises when one leg is extended and the other is raised near the vertical crank angles. Now, this position generates intense counter-rotating vortices that increase drag, originating from the upper hip of the extended leg and the rear of the hip of the raised leg. Now, this flow regime produces a much more disordered wake with higher drag. Now, impact of wake on drag structures. Now, the size and strength of the wake structures changes as the legs move through the pedal cycle, now directly affecting the aerodynamic drag. In particular, the formation of large low-pressure regions on the cyclist's back, hips, and base plays a major role in aerodynamic resistance. Now, these low pressure areas are responsible for between 12 and 20% of the total drag throughout the crank cycle. Over 60% of the drag variation can be attributed to changes in the pressure distribution on the cyclist's back and hips as the legs move. Essentially just causing flow to want to move in different ways depending on where the low pressure regions and high pressure regions are and as they move with the individual's pedaling stroke. Now, much of the current understanding comes from quasi-steady analysis where the flow is studied at a static leg position around the crank cycle. These studies show that large-scale flow structures observed in quasi-steady scenarios still dominate the wake and at elite level time trial speeds and cadences. However, dynamic studies involving actual leg motion confirm that the presence of these structures and suggest that the drag varies throughout pedaling, though the exact point where the quasi-steady assumption breaks down, likely at higher cadences, is not yet known, or at least it's hard when you're looking through publicly issued documents as to really where it kind of is. But from a practical point of view, the cyclist's leg position throughout the pedal stroke has significant impact on the aerodynamic drag, meaning that optimizing pedaling technique and body position could lead to substantial performance gains. Now, whether this is it could link back to crank length and it could link back to position and potentially a pedal stroke where the individual rocks more potentially. Maybe that can have more of an impact as the posterior part of the spine, like the lower part of the spine, is beginning to rock further, and potentially greater leg extension. Maybe that causes greater variation in the flow over the back and the flow around the legs. Now, the aerodynamic wake produced by the cyclist is highly sensitive to changes in body posture and leg movement, suggesting that equipment design, such as clothing and helmet shapes, should aim to manage control wake structures. And the pressure distribution around the cyclist's back and hips, refining the total aerodynamic package used to manage these is clearly important. Now, obviously the fact that we are dynamic objects, not like a car, for example, where, say it's moving in a straight line, it's static, as in nothing on the body is moving, or should be, depending on, how stable everything is. Compared to the legs, it doesn't matter what you're doing. Your legs are always going to be moving. And it adds another dimension of nuisance, let's put it that way. Right, so now we can kind of get on to individual performance improvements, whether it's helmets, skin suits, wheels, frames, rider position. This is probably the bit where most people are interested in. So if you've skipped here and because you didn't want to know necessarily the minutiae of the previous bits, welcome to this part of the episode. If you've been through all of it, I guess this is the bit you're really looking forward to, and thank you for sticking around. So, rider position, let's start with that. So let's start with rider position. The importance of cyclist positioning has driven many wind tunnel investigations into the main positions used by elite cyclists. Now, these studies, reflected in various figures and tables, report the drag area and drag coefficients of cyclists in different positions. Now, generally, the findings from wind tunnel experiments are consistent in ranking the aerodynamic performance of these positions. You think anything you see on from an academic review, all the way really to something in like Cycling Weekly, they usually all conform on what the given best positions are. Like, say, for example, on a road bike, drops being better than Hood's upright, but then Aero Hood's parallel forearm position being the Dan Juan. The time trial position shows the lowest aerodynamic drag, followed by the drops position, while the upright positions, such as the hoods and stem, exhibit the highest, drag. On average, wind tunnel data suggests that moving from upright position with straight arms, such as the bars, the tops essentially, or the hoods position to the drops position, can reduce drag by 15 to 20%. The time trial position can offer even greater drag reductions by as much as 30 or 35%. That's where kind of the time trial bike comes into its own. It's not that, whack drop bars on a time trial bike and it will be like ludicrously fast. It's more the position the time trial bike allows you to be in with the aero bars essentially. Now, these figures are averages, and there's a considerable variation in the measurements of drag area and coefficients for the time trial position, with differences as large as 40% between wind tunnel studies and up to 60% when comparing wind tunnel results with indirect drag measurement methods. Now, several factors really contribute to the variations in reported aerodynamic forces and coefficients across wind tunnel investigations. These really include differences in atmospheric conditions, drag measurement devices, wind tunnel types, and specific testing environments like blockage effects and flow quality. Another source of variations stems from the test methodologies used, where cyclists are pedaling or static during tests. Studies have shown that pedaling cyclists can exhibit drag coefficients up to 6% higher than those measured in static situations. Then the crank position, so on and so forth. Now, despite many wind tunnel studies, the large variations in aerodynamic drag observed between cyclists due to rider geometry and subtle changes in position remain difficult to fully explain. Drag is highly sensitive to rider shape and position, making it hard to pinpoint specific rider attributes that consistently contribute to these variations. Now, a study by Zvardvik et al. Explored the drag coefficient for two athletes of similar height and mass, comparing their performance in different positions like the brake hoods, drops, crouch drops, and time trial position. While the time trial position had the lowest drag coefficient, the brake hoods the highest. The study found significant differences in drag between the two athletes, even in the same position, with drag varying about as much as 30%. Now, this is why I did have a conversation with someone at one time who worked for I suppose you could call them an aerodynamic consultancy, and asking about what the design methodology was, so on and so forth, and really just summed it up with a lot of head scratching, and ultimately it's a lot of testing and going with what's faster. You come up with a general idea, whether it's, for example, these aero base layers, for example. You come up with the general idea that you want to test having the ribs essentially, rather than being directly on the material, underneath the material. So you have a smooth aero jersey or smooth speed suit, and then you've got these ribs underneath, and then you just do a very coarse sweep of, you can see it on Rule 28, I believe, where they go large, medium, and small spacing of these ribs. And then from there, you just test on the athlete. If it's an Olympic program, then you ideally test on the Olympic prospect or prospects and come to a conclusion of how you're going to design for that individual. And the understanding, I suppose, is somewhat secondary in the sense that you use the findings from real world and wind tunnel maybe to improve your own in-house models and try understand in a less time crunch, I suppose, less costly environment in between maybe Olympic cycles, to then build upon where you last were. Now, it really is generally the largest contributor, as we said, to the aerodynamics of the individual. And it's easy to see because you go down a hill with your new speed suit, you don't really notice much different. But if you go down a hill in the aero tucked position, you're like, bloody hell, this is a lot faster. Now, other studies have examined the effect of rider position on streamlining with varying results. Gibertini and Grassi found that, in contrary to previous studies, the most streamlined position for one experienced rider was not the time trial position, but the brake hood's position, despite its higher frontal area. Now, this suggests that reducing frontal area alone may not always lead to the lowest drag. The relationship between frontal area and drag is complex, and minimizing frontal area does not necessarily result in the lowest drag. While many aerodynamic principles highlight the importance of reducing frontal area, the other results in a flat back, low tucked head, and parallel forearms tend to reduce drag. However, optimal positioning varies between cyclists, and really, as an individual during the winter, especially if you're doing something indoors, get yourself a mirror, put it on the wall, and essentially what you're trying to do is generate a position that has the lowest frontal area but still looks like you're almost one blob, is the way I describe it, is generating a position where your head is as tucked in as possible and is as close to allowing an inline flow pattern between your head into your back, tucking the shoulders in, especially if you're a wider individual. This can be more important to allow, and then work on holding that position, work on creating that position, and potentially you can try test outdoors, but potentially the margin of improvements is hard to necessarily detect. I mean, if you've got a power meter and you got a flat bit of road and very favorable wind conditions, aka none really, then potentially yes, you can try assess speed for a given power and see where you go from there. Yeah, try work on it indoors, and it's definitely something that will lead to a large amount of improvement. Now for bike frames, everyone's favorite. Now, surprisingly, not much has been published in peer-reviewed articles about the aerodynamics of bike frames. However, Zardvich and Parker et al. Are notable exceptions, as they did early studies on how to improve bike frame aerodynamics. The testing adding splitter plates to around the tube frames, but found that the results were limited, concluding that streamlining the tubing with teardrop or airfoil shapes was more effective for reducing drag than any of these add-ons. Now, Parker and his team showed that adding fairings to close the triangle of an open frame improved aerodynamics through this. It's banned in the UCI regulations. And it's clear why that would help. Obviously, it's another area where turbulent flow is going to be created, and smoothing that out means it's helping to keep flow attached and as laminar as possible, even though the legs are going to be disturbing things. Now, they also pointed out how important rider position is in minimizing drag. Most bike frame development happens in the industry, and details are hard to access, but modern bikes clearly show the impact of aerodynamics, really. I mean, you look at a TCR and you go to places like Tour Magazine and they show how it's like 220, say, watts for their test, and then you've got like an Aero that's like 200 or sub 200 watts. So you're looking at a decent chunk of savings through the frame itself, So it's not that there are clearly no improvements, but the body is still king of improving aerodynamics on the bike. Now, for the past 50 years, bike design for elite athletes has mainly been driven by understanding how aerodynamics affect cycling performance. Advances in materials and the rules set by the UCI. This can be seen in evolution of time trial bikes, such as those used by Olympic gold medalists compared to the older round tube frames used before the 1980s. One early example of aerodynamic bike design came from the Elite Athlete Project by the US Olympic Committee. Ahead of the 1984 Olympics, they developed what became known as the funny bikes for their track cycling team. These bikes have features like streamlining tubes, cow horn, handlebars, and small wheels to improve drafting in team events and rider position in individual races. Some of these designs, like the small front wheel, are now illegal under the UCI, but it's the start of aerodynamics in cycling as you kind of know it now. By the late 1980s, lightweight composite materials allowed for more creative and aerodynamic bike designs. Really, the carbon fiber that we use today, essentially, these composite materials, are what is allowing, because you think these, especially this new age, like if you think of the Ribble Ultra, I think it is, massive tubing on that bike. If that was an Ali bike, it'd be way out of the required weight for like a world tour team in any format. So it has allowed people to design bikes that can stay very close or on the UCI weight limit with drastic improvements to the overall aerodynamics. It's also, companies like Zip and Lotus introduced super bikes with monocoque frames that ditch traditional designs such as the double diamond frame to reduce drag. These frames molded carbon fiber to serve both as a strong structure and an aerodynamic fairing. When tested, these bikes had significantly lower drag compared to conventional designs. However, again, in the early 2000s, the UCI enforced stricter rules requiring more traditional frame shapes for competitions, and in 2009 they introduced the 3-to-1 rule, which limits the shape of the tubes used in the bike frame, and is why unless there is a drastic change in the ruling, you're going to converge soon on like a optimal design, really. And it's why, in essence, you would see stagnation and less improvements, and overall the convergence of bike geometry. And like, for example, drop seat stays, everything's got that now, and the front forks look much the same, and the head tube is much the same, and there's just little nuanced differences between bike to bike, and really that's where it's going to converge. And the bike itself in the TT format is, yes, allowing you to get in the position, but on the road format, yes, these larger dimension profiles and closer to aerofoil-like design is what's trying to encourage. And really, you can see it like the Lotus bike, for example. That's a good example of where aerodynamics is really kind of pushed on. And but again, the biggest improvements in cycling performance come from optimizing the rider's position. Time trial bars, for example, help reduce frontal area and streamline the rider, and are now essential in any competitive time trials. In the 1989 Tour de France, Greg LeMond used these bars, and an Aero helmet gave him a crucial aerodynamic advantage, allowing him to win by 8 seconds, the smallest margin in the race history since the late 90s. The UCI rules have limited frame design innovation, but in triathlons, where the rules are more relaxed, designers have more freedom to push aerodynamic improvement. And modern triathlon bikes now feature internal cabling, hidden brakes, and built-in storage, which is probably the biggest thing, to allow for carrying of nutrition in the most aerodynamically savvy fashion. But that then brings us on to wheel design. We've just done frames, now wheels. This, people love it. and it's where a lot of money gets spent. So wheels are a big part of the bicycle design and have been studied a lot when it comes to cycling and aerodynamics in general. The aerodynamics forces acting on wheels can change quite a bit depending on their shape and design, whether they're spoked wheels, deep rim wheels, or disc wheels. And the conditions they are used in also plays a large impact. Now, research on the aerodynamics of spoked wheels actually started in early 20th century, originally for aircraft with fixed landing gear. Obviously, that's a big source of potential drag, and especially at the speeds they're going at, it would make sense. Now, from there, bicycle wheels have a different form with a larger ratio of wheel diameter to tire diameter, which affects how they perform at high inflation pressures. Now, in the last 15 years, several studies have focused on how wheels behave in yawed flow, which essentially means the angle at which the wind hits the wheel. Now, these studies looked at a different type of wheels, including spoked wheels with deep rim profiles, unconventional spoke designs, and disc wheels. However, much of the detailed research on wheels is proprietary or published in unreviewed reports. Some of the research, though, has been done using wind tunnels and more recently computational fluid dynamics, which allows for more detailed analysis of how air flows around the wheels. This is one thing for me. Obviously, you've got Tour magazine, which kind of publishes the bike-only performance with a waist down dummy, static dummy on the bike. But obviously the wheels on them are the wheels they get shipped with, and so you can have wheel depth and quality of wheel and interface with tire and so on and so forth that are affecting things. It would be great if someone with a bunch of money independently went and just simply tested all these things, whether bikes, skin suits, helmets, so on and so forth, and published it. The reason it probably doesn't happen is because how much value is there necessarily for that individual outside of their own interest, unless they're just filthy rich, essentially. It's an expensive task, and there's a lot of kit out there, and it's ever kind of growing. Now, one wind tunnel study by Tu and Sayers. Actually, let me go back a second. The reason I mention that is more because, like some of the papers say and reference, that a lot of this stuff is unreviewed. By that, it literally just means that when Rule 28 or No Pins or Specialized or whatever have these papers that they publish or blog posts, it's obviously the validity of the individual. I think Rule 28 have said it themselves in a Trainer Road forum, is that often, especially with like base layers, everyone's base layer is better than everyone's when they test it themselves with their skin suit or whatever. And so it's kind of hard to some extent to really cut through. And unless you see drastic changes, which usually is no skin suit to skin suit, the minutiae of which one's faster, outside of testing and purchasing all of them, you just have to make your best judgment as to what you deem more valid, or potentially what rider it was designed for. Like if a helmet was designed for a bigger rider and you're a smaller rider, try find one that was designed for a smaller one. Like if you just find a rider of your sort of geometry and see what helmets they get released around them, for example. So yeah. Now back to the wind tunnel study. This study examined 6 types of wheels, including conventional spoke wheels, bladed spoke wheels, and disc wheels. They found that disc wheels reduced drag by 70% compared to traditional spoke wheels in straight-on conditions, while deep section wheels reduced drag by 60%. And then these deep section wheels also had a consistent drag across different wind angles and speeds, but the disc wheels showed a sharp increase in drag at certain angles, especially at low speed. This sudden rise in drag was linked to the boundary layer separation effect, where the airflow around the wheel became unstable, which you don't have to worry about. You have to assume if you're running a disc wheel, it's because you're going fast, and also the yaw is getting smaller because simply you're going faster and you're resulting in essentially the free stream air to some extent being forced to hit you in a lower yaw angle. And I thought this was a good point to put, is the fact that the disc is 70 and the deep section is 60. Now, what the actual deep section was, not 100% sure, but essentially what it shows you that even if the disc is, even if the deep section is a 60 mil, there's still a lot of material between a 60 and a full disc. So it kind of shows you where the difference between potentially an 80 and a, let's say a 50 is probably somewhat marginal, and you don't necessarily need to run a super outrageously deep wheel set on your bike. Now, CFD, on the other hand, particularly by Godot et al., has provided detailed insight into how different parts of the wheel, like the hub, the spokes and the rim, contribute to overall drag. So essentially like a loss cascade of sorts of how each component contributes. Now, these simulations show similar trends to wind tunnel data, though exact comparisons are difficult due to variation in testing methods. For deep profile wheels like the Zip models, the drag was lowest at yaw angles of 10 degrees, while conventional spoke wheels showed flatter drag curves. Disc wheels performed better across a wide range of angles, though the study could replicate a manufacturer's couldn't, of a net propulsive force at certain angles. The analysis also revealed complex flow patterns around the wheels, suggesting that airflow disruptions caused by the spokes play a key role in drag reduction, though more research obviously is always needed. But essentially that's why you get these different spoke designs, these Aero spokes. Really, again, looks like the big player in all of this is just having some increased cross-section to the wheel rather than a going from like the box section alley wheel. So really, it means that as an individual, you can do a bit like, so I, myself, rim brake bike, just went for a second-hand set of the factory giant carbon wheels. Obviously, there's a weight penalty versus buying something fancier, but to be honest, these things cost about £200 second-hand. So it's somewhat of a no-brainer. It gets me the deeper wheel. It gets the apparel effect of it, and it's not breaking the bank. Having to have the cutting edge, as you can afford to lose watts here and there, like half a watt here or there. Yes, it may add up to 5 watts, but as an individual where you're not necessarily hyper elite by any description and are really constrained by hours to train and funds, potentially just getting the depth is all you're after for the time being. Onto helmets. The position and size of a rider's head compared to the bike and the rider system mean that the type of helmet they wear can greatly affect the overall drag they experience, as I kind of mentioned before. People have become more aware of the impact of aerodynamic drag on performance. Helmets initially designed just for safety and ventilation have evolved into specialized time trial helmets focused on improving the rider's overall speed. Now, recently, hybrid helmets have been developed to reduce drag while still provide good ventilation and mobility. This attention to helmets is because the rider's head and helmet have a large impact on total drag, with some studies showing that the difference between good and bad helmets can be even greater than the difference between fast and slow wheels. Usually you don't have to look that far for a test or a watts per dollar or watts per pound and find that helmets are usually pretty high up there. One, because they offer potentially greater improvements than wheels, and two, costs compared to like £1,000 set of carbon wheels versus a £300 or £200 Aero helmet is usually quite, it makes it a lot easier for the helmet to be more worth it. Now, long-tailed helmets, which extend behind the rider's head, have been the focus of many studies. Now, these studies looked at different helmet designs, how they're worn, and how they interact with the rider's head and back. Blair and Siddelk studied 14 time trial helmets using a mannequin and found that well-performing helmets can reduce drag by up to 10% compared to poorly performing ones. They also found that high inclination angles increased drag, but there were no clear links between helmet design and performance. Now, that's probably where it comes into this whole individuality, and you could test 3 riders with the same helmet, and one rider you could think, wow, this design methodology we've got here, unbelievable. But then the next rider it goes and you discover that, they've lost it completely now. Others have found that rider posture plays a big role in helmet drag, with a more upright road posture creating more drag than a low time trial posture. They also showed that visors help reduce drag, while forward-facing vents generally don't increase it. Brownlee's research showed that in some cases, visors or sunglasses slightly increase drag, but overall time trial helmets have better aerodynamics than regular helmets, or even the mannequin/human head. And that's where visors come in. It's that cleaning up of the face region and further kind of smoothing that out and allowing for, again, this flow to remain attached, as is essentially been the running concept from start to end of this episode. Now, other studies have been conducted at detail where wind tunnel studies to examine the airflow behind 3 long-tailed time trial helmets. The helmets also all produce similar drag, but the study didn't explain the specific factors behind the performance. So it's sometimes unclear really where it's coming from, but all you essentially need to know is helmet design varies depending on the helmet's shape and how it fits the rider's head and back, and it at some point will have been designed around a rider. Now, if it's a kind of full-blown, I don't know, like a road helmet, how much they are designed around an individual rider, I'm not sure. Whereas definitely, like, you look at, say, for example, the helmet Garner's wearing, and it's got the little almost dive planes coming off the visor. That clearly designed for a larger, wider, potentially rider. So if that is you follow that. Whereas, for example, potentially the specialized helmets with the sock could potentially have been designed around a slighter, smaller individual like Evenepoel. So if that's you, then you kind of follow in that line, because they're so individual. Generally, you're going to get the benefit from almost any of them. You could go down the route of looking up testing and go with the one that performed consistently well across varying individuals. But ultimately, when it comes to helmets, position discipline is going to be quite crucial, and the more you move around, the worse it's going to perform. And the more you look down, say with a long tail, and that tail's not sticking up in the air, you get the picture. So next, we'll talk about skin suits and their fabrics and why these are potentially also, again, another huge, much more than what would be considered marginal gain. Now, textured fabrics are often used to improve aerodynamics in specifically high-speed sports like skiing, speed skating, and cycling is somewhat there. Now, the main benefits of these fabrics is that they help delay airflow separation from the body. These little like dimples, for example, where the air it helps trap that boundary layer in place and helps encourage flow attachment. Now, this obviously reduces the size of the wake behind the athlete and leads to less pressure drag, making it easier to move through the air. Now, in one of the first studies on skin suit aerodynamics, researchers like Brownlee looked at how different textured fabrics could improve cycling performance. Now, the texture of these fabrics depends on the factors like type of yarn, stitching, pattern thickness, and tension. Over 200 string fabrics were tested in the wind tunnel on models and actual cyclists to figure out what worked best. And they found a few key insights, being arms and legs experience changing airflow. So fabric texture matters for these areas. The legs movement during pedaling and turbulence from the bike can reduce the effectiveness of textured fabrics. Now, smooth fabrics are better in areas where airflow stays attached to the body. In areas where airflow completely separates on the body, like the lower back, fabric texture doesn't really impact drag because it's essentially not in contact with the air. So any material can be used in that area. And I suppose why pinned-on numbers can have less of an impact, because essentially they're not actually, potentially the airflow is not being attached to that region, but obviously there's still an effect. Now, tight fitting clothes with minimal wrinkles and seams aligned with the airflow reduce drag. Using these findings, they tested a cyclist in a wind tunnel and found a drag could be reduced by 4% when using a skin suit made from 5 different optimized fabrics compared to a traditional suit made from only 1 or 2 types of fabric. So that's on the finer end where the fabric is making the big difference. But the key bit there really is the tight fitting section. It is going to be the biggest driver of this performance increase. Now, the way turbulence interacts with the body at lower speeds is crucial to skin suit performance. The human body has areas that behave like cylinders, such as arms and legs. So the research into airflow around cylinders has influenced skin suit design. One study found that rougher surface textures on cylinders can reduce drag by causing airflow to stick to the surface for longer. This is where you see in maybe the last gen of skin suits that they had like a rough texture on the arms, whereas now they've moved to this smooth texture on the arms with the Aero base layer. And it's why definitely, for example, you can look up Rule 28 and you see that their previous gen suit with the rougher textured arms is actually faster than their smooth textured skin suit when not worn with the Aero base layer. Then when it's worn with the Aero base layer, it's improved. But that's probably where that comes from, essentially. Now, similarly, the aerodynamics of the body depends on factors like the size of the athlete, cycling speed, air conditions, and rules set by cycling governing bodies like the UCI. However, simplifying the body as just a series of cylinders doesn't fully capture how air flows around the rider. The interactions between different body parts and how they move plays a big role in aerodynamic drag, and hence why the full picture needs to be assessed. And outdoor testing ends up being / velodrome testing, where you got the full individual dynamic environment and you can really assess what's faster. Now, other factors that affect drag include the angle of the rider's body, wind direction, and turbulence in the air. Studies show that increased turbulence can cause drag reduction to happen sooner. But the effects of turbulence on real-world cycling are still not fully understood. Because of this, there's no single skin suit that works best for all riders and conditions. And each suit has to essentially, that's why at the elite level you get tailored suits. And this isn't to suggest that an amateur needs to go get one. The amateur just needs to make sure that their version of tailoring is just getting one that, fits well. Like doing the measurements properly, ordering it, trying it, and making sure that when you ride in it, essentially there's nothing's flapping around. Everything's tight, everything's in the right place. And even it being too small, where you've got like a wingsuit essentially on in the armpit area between that part and the lats, make sure that's not happening. And then just the common one usually is the around the trap area that can start flapping around if it's not really like well fitting, for example. Now, a lot of the time I find when looking at aerodynamic stuff, it's all very time trial focused, because it's the only time really a cyclist is competing and on their own against the wind for such a prolonged period of time. But you have to think that air doesn't just vanish when you're in a bunch. So, and also it becomes quite important, drafting that is, when you're in a breakaway. Usually you're not a solo breakaway. Usually you're trying to hit like a critical mass, say 6 riders, where you now, if you're all motivated, you can outperform the bunch. Now, drafting or riding in someone's slipstream is a key strategy in most types of bike racing, except for, as I said, individual time trial events. Now, drafting allows riders to cut their own air resistance by riding behind another individual. Despite how common this is in racing, there's not actually that much research on how drafting works, mostly because of its tough measured and model. Now, not how it works as in what's going on, but like the nuts and bolts of the effectiveness and how to optimize, for example. Now, the advances in technology have allowed scientists to start digging into how multiple riders affect each other's aerodynamics. In events like the team pursuit, which is probably the area where you would say it is most important to have a consideration for the effect of drafting, because you very rarely in a road race are you drafting your own teammates in a scenario where you're up the road, where you can orchestrate a formation. Most of the time you're drafting. The only time you can really think is the bunch, maybe sprint at the end, where yes, you're in that draft, and that's similar to like a team pursuit kind of environment. But in the team pursuit, where teams of 4 riders race to complete a track as fast as possible, the goal is to minimize drag not just for yourself, but for your teammates as well. Now, riders consistently rotate who leads, allowing others to benefit from the reduced air resistance behind them. Researchers have studied questions like how much drag is reduced based on the distance between riders, and how much benefit the trailing riders get, and whether the lead riders also see any drag reduction. Now, studies show that riders follow closely behind another can experience a significant drag reduction of often between 15 and 20%, depending on how close they are to one another. As the gap increases, the benefit decreases, because that wake is getting filled in, and once you're about to bike length away, the drag reduction drops quite sharply. So it's a very close situation where you need to be in to maximize the drag reduction. Now, interestingly, even though the air conditions are different for a rider in a drafting position compared to one riding alone, the overall shape of the air wake behind them stays pretty consistent. There are some differences in how much drag reduction varies from study to study, but it's largely due to differences in the rider's size, shape, position, and skill in maintaining a close draft to the other individual that affects their performance in the draft. Now, the closer and more in line the riders are, the greater the benefits. One early study using a coast-down method found a similar relationship between drag reduction and drafting distance, though it was a bit inconsistent due to the difficulty of maintaining a constant gap between riders. Now, other studies have looked at how individual riders' characteristics affect drafting. For example, larger riders tend to prove a greater draft benefit to those behind them. However, there's also some interaction between the specific riders in the group and drafting skill. How well riders stay in the draft plays a big role in the overall performance. Now, some wind tunnel studies removed the human element by placing dummies or controlled riders in specific positions to better understand drafting effects. These studies found that shape, size, and position of the riders all, of course, matter, and that drag reduction decreases quickly as the gap between riders grows. Riders who are positioned laterally, so side by side or slightly offset from each other, experience less drag reduction, and in some cases both riders may actually experience more drag than when riding alone due to their interference with one another and their effect on each other's wakes, essentially. One interesting finding is that not only do trailing riders benefit more from reduced drag, but the lead rider also experiences a small drag reduction around 1 to 3% when riding behind them when they're riding behind them and close enough. This happens because the trailing rider's present increases the pressure in the wake of the lead rider, reducing the pressure difference that is created and reducing drag. Now, it's just because essentially you imagine that CFD we spoke about earlier, where you've got the red and the blue patches. Now there's a red patch in front of the trailing rider, so that's essentially impacting the pressure in that area behind them and therefore improving the overall drag. Now, further studies looked at the effects of vehicles following cyclists, which you will see any UCI time trial, such as so when a car or a motorbike follows closely behind a cyclist, it can reduce the cyclist's drag by up to 10%. Like, honestly, when I saw it, it's an alarmingly large number, I guess, given how big a car is, and relative to the size of the car, the distance to the rider is quite small. So This is significant enough to impact race outcomes. For this reason, they've been calls to increase the minimum required distance between following vehicles and riders in professional races. As for team dynamics, when multiple riders are in formation, the third rider often sees the greatest drag reduction, with subsequent riders experiencing diminishing returns. On average, the second rider in line typically gets 30 to 40% drag reduction, while the third and fourth riders can see reductions of up to 55%. The lead rider benefits slightly more from the presence of those behind them, and each trailing rider not only benefits from reduced pressure in front of them, but also from high pressure created by the rider behind them. So it's just a snowballing effect. So yeah, make sure you got like at least 6 of you in this breakaway. But yeah, so really, to keep it simple with drafting, the closer you are and the more in line you are, the better. The bigger the person in front of you, the better. And, you know, the more of you there are in the break, the better, not only for the amount of energy you've got to put in and how frequently you've got to put it in at the front, but also the fact that now you're just benefiting each other even more in this well-orchestrated pace line, hopefully. So that brings us to the end of this episode. Bit of a longer one than I've done for a while. I guess maybe just particularly been looking forward to this one for a little while. Taking a while to just kind of get the different resources and just see what the literature said, because really obviously from studying engineering, had some aerodynamic background. However, specific to cycling, a lot of the stuff is very surface level that you find on the internet and just tells you how many watts X piece of equipment gives you back, really. So it was interesting to read some of these different papers and see what the results kind of say. And some of it's kind of self-intuitive, some of it less so. But I think really from it, you can get the key takeaways that anywhere else will tell you. And that is that rider position is king. After that, really, your helmet and skin suit are key. So say you're a TT rider, really TT bike first to get the position, then helmet and skin suit. And then after that, you can start getting wheels and stuff like that. But even on the wheel front, if you can get some second-hand 88s or something, just stick with them. And then if you want a disc wheel just for a bit of a benefit, then you can get it. But it's not necessarily the most important thing. Your position discipline, and then fabrics and helmet, and that are going to be the key things that are going to determine your overall performance. So what's your takeaway from all this then? Feel free to share it at the vo2lounge@gmail.com or the VO2 Lounge Discord server, or even the VO2 Lounge Instagram, where you can DM me with your thoughts on this episode. For more content like this, explore my previous episode and consider following and rating and sharing the podcast wherever you get your podcasts from. Thank you for tuning in, and until next time, it's goodbye.